Good afternoon. Thank you for the opportunity to present this project at the annual MTV meeting. My name is Alex Glaser, and this is a joint paper with Eric Lepowski, who is an MTV fellow, and Jihei Jian, who is an MTV associate. And both of them also have posters at this meeting. So, confirming the absence of nuclear weapons via passive gamma ray measurements. Now, this work is primarily relevant in the context of nuclear arms control. So, let me just very briefly summarize where we are today. As you know, the New START treaty between Russia and the United States was recently extended until 2026. The treaty limits the number of deployed strategic nuclear weapons to 1,550 on each side. Now, the treaty has extensive verification provisions. In fact, the inspection annex, which describes all verification procedures, has more than 90 pages. New START verification is based on declarations, data exchange, notifications, and a limited number of on-site inspections. There are 18 inspections allowed per year and per party. Now, the only specialized piece of equipment used for verification purposes under New START are neutron detectors, and they are used to confirm the absence of treaty accountable items, or in treaty language, to confirm the non-nuclear nature of an object. Here you can see the US version of this detector. This is the second generation version developed by Sandia National Laboratories. And it has been used since 2018 for New START verification. Here's an older version of a similar detector. Again, this is a modified Eberlein ESP2 detector, and all it does is it counts gross neutrons. Now, in the paper, we suggest that similar instruments could also be used to verify what has been called all warhead agreements. The US in particular has expressed a strong interest in pursuing such agreements, which would then include both deployed and non-deployed weapons. It could be a bilateral agreement, it could be a multilateral agreement. But fundamentally, we could be building on the experience with New START and confirm compliance with such all warhead agreements. And again, using absence measurements and with minimum access to treaty accountable items. So fundamentally, a party would declare an item as a weapon. It would sort of get credit for that. But it would then have to confirm that additional items that may be present at the site are in fact non-treaty accountable or non-nuclear in nature. We'll just point out that similar inspection systems and approaches could also be relevant in other nuclear arms control contexts. Now, of course, as you know, neutron detectors are good for detecting plutonium. The presence of plutonium, they cannot be used to detect the presence of uranium, which does not emit neutrons in significant quantities. So fundamentally the question arises, so what do we do about situations where we expect that in fact non-plutonium items may be present? And this is where fundamentally our idea comes in, where we said, well, can we use gamma ray measurements to confirm the absence of kilogram quantities of plutonium and uranium? And I should also emphasize that we see this approach as a possible complement to neutron measurements, not as a substitute. Now, here's a summary of the fundamental data. We had to sort of choose certain quantities that we want to detect, or we want to kind of confirm the absence of these quantities. So we picked some numbers. In the case of plutonium, we picked 1 kilogram. And in the case of uranium, we picked 4 kilograms. Now, in the case of plutonium, plutonium-239 is the most important isotope. It has several prominent gamma lines between 300 and 500 keV, and this is what we're trying to detect. In the case of uranium, we assume highly enriched uranium, which has a high content uranium-235 and a lower content in uranium-238. And again, we summarize the most prominent gamma lines here. As you probably know, it's actually not the uranium-235 that is most visible with regard to gamma emissions. It is in fact uranium-238, which has a strong gamma line at 1 MeV. And again, we would try to actually find the uranium-238 line in our spectra. Okay, the first thing we can do is to use the standard equations to determine minimum detectable quantities of plutonium and uranium versus measurement time and shielding. In this case, we actually fix the standoff distance from the source to the detector. We chose 70 centimeters. And here you have the results when you apply the relevant numbers and use them with the so-called Curry equation. Lots of lines for different cases that we looked into. Just to illustrate what's going on, let's discuss a specific scenario. Let's say the inspector selects a container for inspection that the host considers sensitive. So the host does not want to open or cannot open this container, even though the content is not 3D countable. The host also knows that the configuration introduces 1 centimeter of lead equivalent shielding and can then propose a measurement time. In this case, the host proposes 5 minutes. Now, if you look at the chart on the left, we have 5 minutes. You can check where it intersects with the line for 1 centimeter of effective shielding, and that depends on the background that prevails in the environment. And you can see that the minimum detectable quantity would be 2 kilograms of uranium or HU in this case. Our threshold is at 4 kilograms of HU. The system should be able to confirm the absence of 4 kilograms of HU in this particular situation. Now, let's just have a look at a different situation. Let's assume the container actually introduces 3 centimeters of lead equivalent shielding. Again, if you look at the chart, you would then see that in that case, 5 minutes of measurement time would not be sufficient to confirm the absence of 4 kilograms of HU. So the measurement time would have to be increased, and of course the host should have known that and propose a longer measurement time in the first place. Now the dilemma, of course, is that the inspector doesn't know the amount of shielding in the container, and we assume that the amount of shielding is sensitive. The inspector, by the way, also does not know what the background level in the facility would be. So the challenge now, or the task, is to develop a verification protocol that can capture all these constraints. So here's our idea or our proposal. It has 4 steps, and it begins with a simple background measurement. So the inspection device would be brought into the location where the inspection will take place. There's a background measurement. Next, we introduce a reference source that is placed at a certain location away from the detector. And the system can then confirm both the presence and the strength of this reference source. And what we use is a simple cesium-137 check source. And our system will try to identify, locate the 662 keV line of cesium-137. So that's step 2. And then finally, in step 3, we introduce the container or the item that is to be inspected. And we move it in between the detector and the reference source. And the idea, of course, is to estimate the amount of shielding that is introduced by the container. So we're looking in the same region of interest, and we can now estimate the amount of shielding in millimeters of lead equivalent introduced by the item. And then finally, we remove the reference source, and we're now looking at the container alone. The system looks for plutonium and uranium in separate regions of interest. As I mentioned before, in the case of plutonium, we look at a window between 300 and 500 keV, and possibly also americium-241. And in the case of uranium, we look for the 1 MeV line of uranium-238. So altogether, we're collecting a few numbers: background, strength of the reference source, the attenuation of the reference source, and then the counts in the regions of interest for plutonium and uranium. And based on these data, the system then reports one of three outcomes: absence confirmed, anomaly detected, or inconclusive result, which could both be a result of not having a sufficiently long measurement time, excessive shielding, or very high background levels. So, but in any case, it should be able to correctly choose one of the three inspection outcomes. So let's look at an example. Here you see simulations or results from a simulation for a shell of plutonium. We also have in the paper similar results for a shell of uranium. There are lots of lines here in this chart, so let's perhaps focus on the regions of interest first. Shown in gray is the region of interest for the reference source, cesium-137, around 662 keV, and you can see as we increase the shielding in the container, the gamma line gradually disappears, and we can use this information to estimate the amount of lead equivalent shielding in the container. And then in the region of interest highlighted in red, that's the region where we are looking for plutonium, and in this case, you can see it's relatively easy to detect the activity in that region of interest. The table on the right shows some numerical data. This is for a 10-minute measurement. You can see the number of counts that we anticipate or expect in the detector, and the system correctly identifies an anomaly. In fact, in this case, it only takes a fraction of a second to come to this conclusion. Now, one aspect that I wanted to highlight is we think such a device and this measurement approach is actually quite interesting, not only for use cases, real use cases, but possibly also for inspection exercises and also teaching purposes. And in fact, we have developed most of these ideas as part of a course that I taught in the spring of 2020 at Princeton University, and both Eric and Jihei participated in this course. As you know, around spring break last year, we went into lockdown. This was a hands-on course, so it became sort of a question: how are we going to finish these projects? And so here I just show you a few examples from our lab. We managed to connect the detectors to via Ethernet to the network, and students were then able to remotely access these detectors. Two different setups, one with and without shielding. We also had webcams where students could sort of monitor in real time what is happening. So an interesting aspect to sort of teach a course like this remotely. Of course, we also don't have uranium and plutonium available in the lab. And again, here, I think it's quite interesting to see that you can easily switch the algorithm to sort of work with different regions of interest. In our case, we chose barium-133 to stand in for plutonium, and we used cobalt-60 to stand in for uranium-238. And here's kind of an actual measurement where you can easily see the cesium-137 line and also contributions from the barium 133. And all you have to do really in the algorithm is change a few numbers, shift the regions of interest and change threshold values, but everything else stays the same, and you can literally switch from one to the other within seconds. Wrapping up, expected impact and next steps. We do believe that systems like the one we discussed have real promise for future arms control verification applications. Building such a portable version, or building a portable version of the system, should be relatively straightforward. Since we're dealing with absence measurement, hardware certification, authentication is much less of an issue. And in particular, a verification regime based on absence measurement would never be exposed to weapons, so safety and security concerns would be dramatically reduced. We hope that a system like this could be field tested in a future inspection exercise, and perhaps, hopefully, this would then also be an opportunity to develop the concept further and enable red teaming of the proposed verification protocol that we discussed in this talk. I'd like to say thank you to all 14 members of the MTV team. The work was partly funded by MTV, and we thank NNSA and the DOE for the continued support of our research activities. And with this, I'm happy to field questions. Thank you.